All right, we're going to start this lecture off on number 51. We just finished up that previous problem. We were looking at just kind of relating one reactant to a product or another reactant or another product, however the reaction is set up. But we're looking at 51. And how I've set this one up so far is we have two sets of data, and this is going to reflect on a problem we did previously in the examples. The gas phase decomposition of NO2 in this particular reaction is studied. So that's kind of how it's focused. It's focused on that. At 383, giving the following data. So I have time and I have concentration of NO2. We are trying to figure out first, is the reaction first order or second order with respect to the concentration of NO2? So again, that is how the reaction is based. If I want to put kind of like an order thing in here, I'm going to call this zero order. But I need to make up two new columns. So natural log of the concentration value based on that change in time, and then the inverse value of the concentration based on that value again, and then see how these numbers in. So I'm actually going to not put these in. I'm going to be a little lazy and just use my calculator to produce those sets of values, and then I'll just run them and get the R values, and I'll be able to tell that way. Okay, so let's go ahead and set that up. So I already went ahead and put in the values. Let me get the glare off this a little bit. And I have the values setting in there for the times and the concentrations. I'm going to set up, just so I can show you again, the way to get where I want list 2, the natural log of list 2. So here we go. I'll say natural log of list 2. And I have that one in there. I'm not going to do anything with it right now. And then I'll do the inverse. So I will say list 2 again, inverse. Whoops. Go back in there. Back in. Go back up here, list 4, and then I will say list 2 inverse. There we go. Okay, now I'll go into the calculate. And for linear regression, I'm going to do time versus the concentration first. So I'll say list 1, comma, and list 2, run it. And there's my R value, 0.779. I'll write that down. 0.779. I'll run this again. So stat, calculate for list 1, comma, list 3. And I get negative 0.924. So that seems fairly good, but not great. Let's see if we can get even better. Calculate for list 1, comma, list 4, and again, pretty much 1. So I'll put 1, 0, 0. So it is second order in regards to the reactant in this case. So is the reaction first order or second order? Second order with respect to NO2. All right, fantastic. What is the rate constant? I'm actually going to write that in here first. What is the reaction order with that concentration? So I'm going to write out the rate law. And again, rate laws only include reactants. Here's the K, and then NO2 second order based on that. So I know the rate law. I can put any concentration in here as long, of course, I know it's a rate constant, and determine this. So it says, what is the rate constant? Okay, so how would I figure that out? Well, if we go back and take a look at our line on there, we can figure out what is the slope. And based upon an equation we wrote down earlier, let's go ahead and write that out right now. so we can kind of see it. We wrote this in our notes earlier. This is the equation of that line we just figured out the R value for. Given this, y equals mx plus b, having this set up, what is the rate constant? Rate constant is the slope. So if I go back and look on my calculator, go ahead and write that in here first, m is equal to the slope that we know, and of course that is equal to the k value. And if I go ahead and take a look at my calculator, the a in y equals mx plus b is 10.16. So k is equal to 10.16. But I need some units on here. Okay. Well, remember, as far as putting that in here, rate every single time is molarity per seconds. And then K is what I'm trying to figure out. But if this is concentration on the inside, and that's what I have, this has to make this true from here. So it looks like I'm going to be molarity minus 1, or per molarity, per seconds. So that's it. That is our answer for that particular problem. Let's go over to C. If you use the method of initial rates to obtain the order for NO2, predict what reaction rates you would measure in the beginning of the reaction for initial concentrations. Boom, boom, boom. All right. So to figure this out, we're going to think again. So reaction rates typically many times are figured out given an initial concentration. So I have these initial concentrations sitting here. I have a working rate law hanging out right here. So I can simply put in the rate law, or excuse me, the concentration initial here. I have the rate constant here, and so I just have to calculate it out given that equation. So let me just write out rate is equal to K, and I'll go ahead and just put in this little concentration there, and 2, and I'm just going to substitute this K value in for that. Given that, for the first part, it would be 0.4 per molarity per seconds, or the first one, and I'll just go ahead and write the other ones in here. I'm not going to go ahead and spend a lot of time putting those in here. 0.1, not per molarity, excuse me, molarity per seconds. Molarity per seconds for the second one, and the last one would be 0.025 molarity per second on the last one. And that one's done. Okay, let's bounce over to the notes and see if we can knock out a little bit more for this lecture. All right. This is kind of like some setup work, so we're not going to, well, actually, no, I'll back up. This one here, we'll just look at some half-lives, and then we'll go from there. So half-life of a first-order reaction, and you probably heard of half-lives before, and maybe use it, I think, like in econ, but this is very, very similar to that. If we take a look as far as an equation to set this up, and we take the half-life of a first-order reaction. So if I know the equation for a first-order reaction, here's my initial concentration, but half. So I have the initial concentration. I'm using the rate law, which was set up. We had an equation for it a long time ago. So I'm taking the initial concentration, and then over some time, you have this written down, I'm substituting, so half of that original concentration. If I do that, the other part of the equation which was written is this. So of course these guys here would cancel out because it's the same, and you're left with natural log of 1/2 is equal to the same stuff that was already there. And then if I take the natural log of 1/2 and then just kind of put things together, but you express it in regards to time, because I want half-life in time, I would have 693 over K. And the negative cancels out because it comes out in the math over there. So interesting for this particular reaction, I don't even need to know what the concentrations are. I just need to know what the rate constant is. If I know what the rate constant is, I can plug that into the rest of this equation and tell you what the half-life is for the reaction. I don't need any concentrations. Done. Now just to express, this was first order. To tell you what it is for second order, I don't think we're going to use it, but we'll write it down anyways, just because it does exist. It's 1 over K concentration of initial concentration. And for 0 order, it is concentration initial over 2 rate constant. And that's it. All right, so that'll be the end of this lecture, and we'll start on a whole new topic for the next one from there.